Okay, let me talk about the binomial distribution. And this is related to a random variable x, and we usually write something like this: binomial and p. So we need two parameters. N is just a natural number, 1, 2, 3, etc., and p is a number between 0 and 1, some kind of probability. A typical way of talking about the binomial distribution, it's in terms of coin tossing. And so you want to toss a coin which is biased, so a biased coin that has a probability p of turning up heads. And we toss it n time, and then we count the number of successes, where by success we mean heads, right? So toss a bias coin n times and count number of H's. Okay, so a typical outcome is, let's call it little omega. It's a string: head, tails, tails, head, tails, etc. Tails of length n. Right, so it's a string of length n, and each because of each toss being unrelated to the previous one, we can actually write the probability of this one outcome by looking how many heads, how many H's there are, number of H's, and then take p to that power, and 1 minus p to the number of tails. Right, so if we want to then get a probability that the number of heads is k, some fixed number k, well, we need to look at p to the k 1 minus p to the n minus k, but this has to happen for every possible combination here that has exactly k heads in n tosses, and that's where the binomial coefficient n choose k comes in. N choose k is the number of ways of writing a string with k heads, a string of length n with k heads. Each such string has this probability, and so we multiply them together. So this is for k up to n. So this is what is called the binomial distribution. Okay, let's check that it's a distribution. So let's see that it adds up to 1. So we need to sum from 0 to n choose k, p to the k, 1 minus p to the n minus k. Okay, luckily we have the binomial theorem. So the binomial theorem tells us that this is the expansion of p plus 1 minus p to the power n. Okay. But now p and p cancel, you get 1 to the power n, which is just 1. Okay. Likewise, I claim that the expected number of wins in n tosses, which by definition is the sum k goes from 0 to n of k probability that x equal k. I claim that this is actually just p times n, which kind of makes sense if you have, say, a 50% chance of winning every time and you toss n times. You expect to have n over 2 wins. Okay, so let me give you two approaches to this computation. The first method 1, it goes as follows. It's just a straightforward computation. So first of all, let's start the sum at 1, because we don't need to start at 0, because when k is 0, this is 0. So we can start at 1. And then let's put in and choose k, p to the k, 1 minus p to the n minus k. Okay, we need to sort of figure out what to do with the binomial coefficient, which is n factorial over k factorial n minus k factorial, p to the k, 1 minus p to the n minus k. And well, k cancel out with the first term here, the k factorial term, and so I will get some n factorial over k minus 1 factorial n minus k. And now we see sort of what might happen. We want to rewrite this as a binomial coefficient, but you see the sum k minus 1 plus n minus k is n minus 1. So we'd really want an n minus 1 up there. So we take an n out, right? Take an n out. And while we're doing it, let's take a p out as well, because that's what we're expecting. And so then we have k equal 1 to n minus 1 factorial, k minus 1 factorial, n minus k factorial, p to the k minus 1, 1 minus p, oops, this is k to the n minus k. Okay, and so here we can simply do a change of variable. So I'm going to let j equals k minus 1. This is my change of variable in the summation. And it's kind of like changing variables in an integral, right? You look at the endpoints, k goes from 1 to n. When k goes from 1 to n, j goes from 0 to n minus 1. Right? And then I just substitute. So I have j factorial. Now k is j plus 1. Right? So here I'm going to get n minus j minus 1, which I'm going to write as n minus 1 minus j factorial, p to the j, 1 minus p. Again, this is going to be n minus 1 minus j. Okay, so now here in this situation is another situation where I can use the binomial theorem and write this as p plus 1 minus p to the n minus 1, which is just 1, so times p. So that's the first method. The second method method 2 is to introduce a function. So I'm going to call f of x. I'm going to free one of the variables, so I keep everything the same and choose k. But instead of p to the k, I'm going to put x to the k times 1 minus p to the n minus k. Okay, so you should think of this as a polynomial. And the thing I want, the expectation, is what happens when x is equal to p. Right? Well, actually, I didn't write it. No. So when x equal to p, I get 1, because this is this sum here. This is this sum. So, but let's see, can we relate f to this? Well, if we take the derivative by the power rule, the k will come down, right? So let's take f prime. And of course, when you take the derivative, the constant term, when k equal to 0 here, you get a constant term, that goes away. So you start at 1, then you have a k, and choose k, x to the k minus 1, 1 minus p to the n minus k. This is not quite what I want because of the minus 1. So I can multiply by x, right? So if you multiply by x, then that minus 1 goes away. And now, if I substitute p in it, I get the sum k and choose k, p to the k, 1 minus p to the n minus k, which is the expectation. Right, so how does that help me? Well, by the binomial theorem, I know that f of x is also equal to x plus 1 minus p to the n. And this is easy to take the derivative of, right? So the derivative of that is n x plus 1 minus p to the n minus 1. And so I can then compute p f prime of p sort of directly as p times n, p plus 1 minus p to the n minus 1, which is p times n, because this is 1 here.